All right, our next goal is to look at a set of components that we're going to be working with this week. I have to warn you, this is going to be a little bit dry, but you'll have to bear with it and maybe even refer back to it a couple of times so that you can really understand what these different values are actually meaning. So let's start with our microcontroller. It's an ESP32S3, and the important things to look at when you're looking at these small devices are the processing speed. How much memory do they have? How much storage do they have? What are the interfaces? So this limits what you can actually connect to them, or how many things you can connect to them. Sometimes it's important to look at the dimensions, a little bit less so for what we're working with here. We're not trying to minimize too much. And we're actually going to be using what's called a breakout board here. Breakout board just makes this easier to use. We don't have like the microcontroller itself. We have the microcontroller and everything needed to connect to it, and everything needed to actually make it run from, for example, a USB or a battery. A lot of extra little components packed into this little breakout board. That being said, you also need to know what are the input voltages that it accepts. So this breakout board accepts USB. It also accepts a battery input voltage. You should know how much current is it going to draw off of either of those. And what you see here is at 5 volts, it's drawing 19 milliamps, and at 3.8 volts, it's going to draw 22 milliamps. The next important part here is, well, okay, so that's if you have nothing really turned on. But if you do turn on something like Wi-Fi, you enable the Wi-Fi capabilities of this board, it's going to draw an extra 100 milliamps. That may not be extra, that might be just the total, but I couldn't find an exact answer to that in the documentation. So my assumption here is that this is going to be extra. The bottom line here I also added by digging into some extra specification sheets is that the GPIO, so GPIO stands for General Purpose Input and Out. Input is you reading from some sort of sensor data, and output is you controlling something else in your circuit or communicating with something else in your circuit. And the GPIO pin limit for this particular device is 20 milliamps, which means if you were to plug it into a USB, this is a bit of foreshadowing, plug it into USB and then try to run your motors, you are not only potentially going to damage the USB connection on your computer or laptop or the lab computers, but you're also very, very likely to fry these connections that are on the board itself. So it's very important to note that I never want you to run the motors when connected into USB. All right, so what are some of the important things about this microcontroller? Why did I select this microcontroller? Well, it's small, which isn't the most important thing, but it's also cheap, which was pretty important. It has nice functionality built into it. It has a reset button. It has a user LED, which means we can control when that light's on or off. We can use that for easy notifications, like is the Wi-Fi connected or is the Bluetooth connected, for example. This particular chip also has multiple ways to connect a battery to it. If we wanted to, we could use these 2 pins to connect a battery directly to the microcontroller. We could solder to those pads. That's not how we're going to end up using it, but it's nice to have that as an option if we wanted to scale this thing down even further. Looking at the actual pins on the microcontroller, you might notice that each pin has a list of different names for that pin. And they really are just different names. In code, you could refer to it as A0, D0, GPIO 1, and 01, and it's going to essentially refer to the exact same pin. But you might want to refer to it as D0 if you're using it as a digital pin, or A0 if it's an analog input pin. So that's why they're given different names. You might call this one touch 3 if you're going to connect that pin to a touch sensor, which really in this case would just be a piece of bare wire. One extra nice thing about this board is that it allows you to connect devices to it at 5 volt logic levels or 3.3 volt logic levels. As it turns out, I tried to pick everything to be sort of compatible with one another, so we'll just be using the 3.3 logic level for this class, and we pretty much won't need that 5 volt line, but it is a nice option to have. One last thing to point out here is these extra labels that you may have noticed, SDA and SCL. It means that these 2 pins are going to be pins that we use for some special functionality, some communication between interfaces. A communications interface between multiple chips. So we're going to use those two pins, SDA and SCL, to connect from our microcontroller to a lot of our peripherals. So we will control our display. We will control the motor driver. That's a different motor driver that we're not actually using this semester. But we will be controlling our inertial measurement unit, our distance sensor, and our compass. A lot of different things can be connected to just those two pins for communication back and forth. And if you're curious what these pins are, how these pins are actually defined in code, I did track down the company that makes this. So the company that makes this particular board is called Seed. Actually, I think it's 3 E's, Seed Studio. And they have an Arduino configuration for this board. And they've defined A0 as pin 1. And just to show you I'm not lying, D0 is also just defined as 1. The fact that those are both 1 sort of just tells you those are aliases for one another. And like we saw in the previous slide, SDA is pin 5, SCL is pin 6. This linked GitHub repo that I've got here is actually mostly just in information for getting access to things that aren't as obvious. They don't actually appear on this documentation. So for example, it was the only place I could see that pin 21 was the LED pin. So if we want to turn on the LED, we would do something with pin 21, for example. Alright, well, we're not going to use just the microcontroller. Instead, we're going to plug the microcontroller into this expansion board. And the reason for that is it just adds some extra functionality. Specifically, it gives us a battery port. So that's a battery connector. We don't have to solder our battery directly to the microcontroller, which is a nice extra feature. It also has a switch, which is a nice extra feature, and it makes it easy to connect. Probably hard to see those in the upper left, but that'll be something one of the next diagrams will let me show you in more detail. So what are the important aspects of this specifications table? I think that the one thing that I'd like to highlight here is that if you're going to use the display, it consumes about 15 milliamps. So we'll start adding all of these things up. How much does the microcontroller need to process? How about with Wi-Fi? How about with the display being active? We'll start to collect all of these different values and see if our batteries are actually rated for them, if you're wondering why I keep pointing these out. Alright, well here's just a blown up view of that same diagram. The couple of things to note that are interesting, like I said, we have our battery switch, our battery connector. It's called a JST2. It's actually JST-PH, I believe, 2.0. It says LiPo battery, but it'll also work with our lithium-ion batteries instead of lithium polymer. We have 2 extra ways to connect to our I2C interface. So IIC is another way to write I2C. Also sometimes just put as I2C. That means we don't always have to just connect right directly to pins 4 and 5 here. We can actually plug into these ports. And that's essentially exactly what this is for. It's just making it easy to get access to these ports, these pins. So if you notice D0, A0, that lines up perfectly with our microcontroller here. D0 and A0. And the way you use this board is you plug your ESP32, so the microcontroller, just directly plugs into these first rows, and then these outer 2 rows are what we can plug what are called jumper cables into. So it makes it so that we can easily plug a bunch of things into this thing, into our microcontroller without having to commit to soldering anything, and it means that I don't have to necessarily teach you how to solder and take away class time for other things. And last diagram here for this board is, again, makes it very easy to use with a battery and shut off access to the battery, which means we can power the microcontroller from USB, turn off the switch, program the microcontroller without having to worry about the motors ever being connected directly to the USB. Last little note here is there is an extra LED if you're wondering why that one's flashing or solid green. It has to do with whether or not the battery is actually being charged from the expansion board or not. And I've already mentioned this, but these I2C lines are useful for connecting external sensors. Alright, our next component for which we're going to look at the specifications is our motor. I talked a little bit about it in the first class period, why I chose this motor, so now let's just dig back into some of those details. This motor runs at 6 volts, that's the max rated voltage. You can actually go above that and make it run hotter and faster, but it'll at that point just start deteriorating the performance of the motor in the long term more than we would want. So we're actually going to cap out at 3.7 volts, but it's nice to know that this can take up to 6 volts. If you were to run this at 6 volts with absolutely nothing on the axle, meaning you don't have a wheel, it's certainly not connected to a wheel on the ground, meaning there's just really no torque resisting it, it'll run at 310 rotations per minute, RPMs. And this little golden box here is a 50-to-1 gear reduction ratio gearbox. It takes the shaft, the internal shaft of the motor, and reduces it from 15,000 down to something that's a little bit more useful to us, 310 RPMs. Likewise, if you have it running at 6 volts with no load, it's going to draw 60 milliamps of current. A much more interesting scenario for us is if you're using this in sort of prototypical motor usage, it's going to go closer to 180 RPMs and closer to 170 milliamps. So obviously both of these numbers can change if you vary the voltage or if you change the load. So how much torque is resisting the movement of the motor itself. Speaking of torque, this particular motor maxes out at about 0.8 kilograms per centimeter. One nice thing about this motor is it has what's called a motor encoder built into it. And what we're looking at here is essentially a pinout of that motor encoder. A pinout just means what do the different pins actually mean. So this first pin you would connect to the motor's positive voltage, the last pin to the motor's negative voltage. Those are actually the only 2 pins you need to connect to have this thing move around. The rest of these are used for measuring the speed of the motor. And we do need to connect those just so we don't have bare wires floating around, but we're not going to actually be using those pins this week. We won't worry about measuring the precise motor speed until later. Alright, so I mentioned motor driver a couple of times, and I said we only need 2 pins to drive the motor. I'd like to give you a little bit of information about how motors work. So if we have a voltage source, and we connect that across 2 terminals on our motor, so that would be these 2 outermost pins. We have a voltage, let's say it's 3.7 volts, which is about the voltage of our battery. The motor is a little bit more complicated than what's called a discrete resistor or any sort of discrete component. Its current is actually going to be a factor of how fast the motor is spinning and what the load is on the motor itself. So it's a little bit more dynamic. However, we still have a current flowing through this system. And if the current is flowing in this direction, meaning we have a positive voltage here and a negative voltage here, we are going to rotate this motor shaft in one direction. Let's say in that direction for the purposes of this diagram. What we can also do is take this exact same motor put the same shaft on it, and now reverse the voltage. So 3.7 volts still. And now this side is the negative side, and this side is the plus side, meaning current is going to flow in the opposite direction. what that will do is spin the motor in the opposite direction. To change the direction that voltage is flowing through a circuit, we are going to use a special piece of electronics known as a half bridge. And the way this works is we control a H-bridge with our microcontroller. So we will have our power source, which pretty much looks the same as it did that I have drawn above. So that part doesn't change. And our motor is also essentially not going to change. But here I'm going to draw the shaft sort of coming up the top of it. So we've sort of reoriented the motor a little bit. The way that an H-bridge works is we have 4 switches. And depending on if those switches are open or closed, we can direct the current in the direction that we would like it to flow. So for example, if we want the motor to flow in one direction, maybe I'll leave this one open and this one open, and then close both of these. So here, current is always going to flow from our 3.7 volt battery in this direction. We don't have to rewire the battery like I did here. Instead, under this scenario, current is going to flow in that direction. Same battery, same current on the other side. So it always enters and leaves in that same orientation. However, on this other side, if we switch, or change rather, which switches are open and which are closed, we can change the direction of current. Which means, in one of these cases, our motor will rotate in one way, and in the other case, it'll rotate in the opposite direction. So that's the motivation for this next chip that I have here. This is called a DRV8835, and it is a motor driver. Not only is it a motor driver, but it controls 2 motors. Has 2 separate channels, 2 outputs. We connect our battery source directly to the motor driver, which means we can separately connect our USB to the other side, and we're not going to control these from our USB side. And just like we have 2 outputs, we have 2 inputs. So we have an input for motor A, and an input for motor B, and an output for motor A, and an output for motor B. This motor driver in particular allows a operating range, so a motor, so that the voltage is across the motor from 0 to 11 volts, a maximum of 1.2 amps per channel, so per motor, and that's well within the 170 milliamps that each motor might draw. And we can talk to chips. This DRV8835 is happy to consider anything in this range as logic high. Meaning, what is it considered to be a 1 versus a 0? Like I said, all of our chips are going to consider 3.3 volts high, and this DRV8835 will agree that it considers that a high, which means they can communicate, and they know if I'm sending a bit stream of 100111 it knows that the 3.3 volts should be interpreted as a 1. Hopefully that wasn't too loud. My phone just started ringing and it was right next to the speaker. There's a lot of information for these motors in the motor driver. This is definitely worth reading. It is also 100% not worth me reading to you. This will be in the lecture slides. The lecture slides are on the course website. Please read through all of this and ask questions as they come up. I'm actually tempted to copy and paste this into the lecture slides so it's easier for you to use hypothesis to ask questions. I think I will do so and make sure to update the course website so that you can use hypothesis for questions. Alright, last thing to mention here about the motor driver is its control scheme. So each motor channel, like I mentioned, uses two pins to control it. So why 2 pins? One pin is essentially used for speed. So we have our speed pin and our direction pin. That is wrong. Speed and direction. So how do you read this table? It's written with X phase and X enable and X out, because it applies to both the A channel and the B channel. So this is A phase and B phase, A enable and B enable, and so on. So if you set A phase to 0, that's going to correspond to forward. 1 corresponds to reverse. And the PWM value here corresponds to speed. So if you set PWM to 0, this thing won't move. Which is why, if you set it to 0 here, it doesn't really matter what direction it is. It's still going to be in a braking mode. It won't be moving at all. Alright, so how do we actually use our DRV8835 motor driver? Well, we have here on the left something called a breadboard. This is a really common prototyping piece of equipment, and it's really useful because everything in a row on a single side is connected. All of these pins are electrically connected to each other. Same with all of these, same with all of these. None of the pins are connected vertically. No, none of those pins are connected. Likewise, the pins are not connected across. That's also a no. So, I would say all of these are connected. All of these are connected. But this would be wrong. No, not connected. And same thing here. No, not connected. So when I have our DRV8835 connected here, it's going to slot directly into the pins that it's covering up here and here. If I want to connect my microcontroller into it, I can connect a wire into these different pin slots. And that's how I would connect one piece of equipment to another. Later on in the semester, we'll also be using other portions of this breadboard. So it would be good to, at this stage already, put the breadboard all the way against one side. Alright, our last component, I believe, is the battery. Let's just check our battery and see if it matches all the specifications we've mentioned so far. So this battery has a maximum output of 10 amps at any given time. It has a capacity of 3,500 milliamp hours, so 3.5 amp hours. So you can think of this as if you ran this thing and you were drawing 3.5 amps, you could do so for 1 hour. And as you'll see, we're actually drawing much less than 3.5 amps at any given time, so the battery should last multiple hours. The nominal voltage is 3.6 volts, full charge is at 4.2, the discharge cutoff is at 2.5. You're likely to ruin my batteries if you do them all the way down to 3.5 every time. So for the purposes of this class, I really don't want you going below, like, let's say 3.3 to 3.5. If you see your battery at that level, exchange it with a different one with me, and I'll put that on the charger. This particular battery also has some protection circuitry, so protection IC, protection integrated circuit involved, which should help us stay a little bit safer with our battery usage. Adding all of this up, what do we have? We have two different methods for powering our system. One of them we never want to do with a motor. Never use the USB with a motor. Never power motor with USB. While it looks like the USB port can handle it, sometimes things go wrong, you have a short circuit, you can burn out the port on your laptop. But even worse, you're going to ruin the microcontrollers. Because if I were to flip all the way back to one of those early pages, you would see that the microcontrollers can only supply about 20 milliamps per GPIO pin. So you're going to be drawing way too much from that board. And to be fair, you're not actually drawing motor power from the GPIO pins. They would be coming from the 3.3 volt pin. And I think that one still only has like an output of roughly 100 milliamps. Something in that range. Point being, use a battery if the motors are at all involved. Alright, let's step through this a little bit. We have our microcontroller. Maximum current should be around 150 milliamps with Wi-Fi. And P equals, I times V will give us about 500 milliwatts for that device. The expansion board at 15 milliamps should pull about 56 milliwatts. The motor driver, the specifications are here, but we're not really ever going to be at this maximum value per channel. So I'm not going to add this value in because even though the motor driver is capable of that, and I want that noted in our specifications table, we're never actually going to be close to 1.2 amps. So that doesn't get computed here at the total. The motor driver logic, we're actually powering that motor driver board so that it can talk to the microcontroller, and it's a separate connection than the battery that's connected into it. And it turns out that it doesn't really draw very much, so it's negligible. Same with the wheel encoders, actually. They don't draw enough current for them to show up in the specification sheet, as far as I can tell. The two motors will draw about 150 milliamps at a full speed, and that's just an estimate. So they're at about 600 milliwatts, which means our totals here, 500 milliamps and 1.8 watts. So that's well above what we would want to do from USB. You want to give yourself a safety margin. So the fact that these are about the same, the 500 for the USB and a 500 for our system, means you never want to run all of this off the USB anyway. But we're well within what our battery is capable of supplying. So we shouldn't have any issues with the batteries overheating as long as we're not running them for hours at a time. Alright, this is what we're going to be building up to, this circuit here. So let's step through all these different connections. And we'll start with everything here in the lower right hand side connected directly to the battery. These are wires that are already supplied for you, created by the TAs. The battery is going to be connected to the voltage tester, so we always are monitoring the voltage as long as the battery is being used. The battery is also going to be directly connected to the expansion board. The expansion board, don't forget, has a switch. So we can shut off, just like we have another switch over here, we can always shut off power from the battery to the expansion board and microcontroller. The battery is connected to the switch. The switch is connected to the other side of the voltage tester, meaning we're always measuring the voltage across the battery. And when that gets to about 3.5, I would like you to turn it in and exchange it for a fresh battery. The positive side is also directly connected to the expansion board so that we can power the expansion board and microcontroller after switching on the expansion board's switch. The ground is also directly connected to the motor driver. And then off of the switch, we are connected to the motor driver. So the motor driver will be shut off when the switch is closed. When the switch is open, meaning the circuit is open. So this here is what I was showing like this in the circuit before. And that switch can swing in both directions. We can close it and then open it to shut off current flowing in that direction. And don't forget that this motor driver is actually directly connected into the breadboard. So that's not showing up in the slides, and it won't be showing up in slides going forward, but always worth remembering that that's where the motor driver is actually connected. Now it's time to wire this first part up.